Module 9, Phase Diagrams, Part 4, Eutectoid Reaction. In the previous section, we looked at the eutectic reaction. In the eutectic, we have the liquid separates into two solid phases. In the eutectoid, the reaction is completely in the solid state. We have a solid solution which then separates into two phases. This is the iron-carbon phase diagram, which is very important for understanding steels and cast irons. The line on the right here, you can see that does not represent 100% carbon, but represents 6.7 weight percent carbon. This is the weight percent in the phase cementite, which is the stoichiometric compound Fe3C. This is a very hard material, but it's brittle. On the other side, we have the terminal solid solution alpha, which is known as ferrite. This is almost pure iron and is soft and ductile. We also see another terminal solid solution, delta, and gamma. Gamma has a face-centered cubic structure, whereas at low temperatures, below the eutectoid temperature of 727 degrees centigrade at equilibrium, under equilibrium conditions, below that temperature, the iron exists as a body-centered cubic crystal structure, which has less solubility for carbon. And so the carbon comes out to form the compound Fe3C, which is known as cementite. You can also see within the iron-carbon system, we do have a eutectic occurring here, where the liquid separates into cementite and the high temperature face-centered cubic phase, which is called austenite. Austenite is not magnetic, so if we heat a piece of iron or piece of steel up, which has a carbon composition, which will mean that when it's heated up, it will enter the austenite phase field, it loses its magnetic properties and is non-magnetic. And this can be useful for doing heat treatment or recognizing when the correct temperature has been reached. Let's have a look at a composition of steel, which is at the eutectoid composition. So this is a zoom into this part of the phase diagram. We can see here that at temperatures above 727 degrees centigrade, the material is purely composed of the gamma phase, the non-magnetic phase, the phase-centered cubic phase, which is quite soft. And so we can find the material is quite malleable in this state. However, as it cools, we see because of the limited solubility of carbon in the BCC phase, which is the alpha ferrite phase, we get a separation into Fe3C, cementite, and alpha. And this occurs as very finely divided lamellae, which greatly strengthens the material. This microstructure of the eutectoid is called pearlite due to it looking like mother of pearl under the microscope. So we have 100% pearlite here when we have a steel of the eutectoid composition. The eutectoid composition is 0.76% carbon by weight. You'll notice that this reaction is only possible between carbon compositions of 0.22 and 2.14 weight percent carbon. This sets the carbon composition limits for iron carbon alloys, you could so speak, that form steel. As between these carbon weight percents between these two ranges of 2.14 and 4.3, we have what are called cast irons. Now let's look at what we call a hypo-eutectoid steel composition, where the carbon composition is less than that of a eutectoid steel. We will see that the gamma phase at high temperature, the material is completely in the gamma phase. As we cool down and we hit this phase boundary, MO, we start the precipitation of alpha within the gamma. You can see this occurring at the grain boundaries. The alpha phase grows like so, and the composition of the gamma goes towards the eutectoid composition. At that point, the remaining gamma turns into pearlite. So what we're going to have pearlite regions which are separated by pro-eutectoid alpha. So pro-eutectoid, it's the first phase to form as we cool the austenate, the gamma phase. As a ferrite is quite malleable, this gives us a material that is strong but malleable, otherwise called a mild steel. With a hyper-eutectoid steel, the carbon composition is above that of the eutectoid composition, but less than 2.14, as we still want to have the material in the gamma phase at the high temperatures. With the hyper-eutectoid steel, we can see that high temperatures here at G, the material is completely in the gamma phase. As we go below this line here, PO, we start precipitation of the cementite at the grain boundaries. Cementite is a very hard material, and what's going to happen is the carbon composition of the gamma will reduce until we reach point O at this temperature here, and at that point the austenite will transform into pearlite, and this is under moderate cooling rate. So what we end up with here is we've got pearlite regions which are separated by the pro-eutectoid cementite. This is the cementite is a hard material, and so we end up with a hard material that is brittle, and this is useful for applications where we want to be resistant to wear, such as tool steels, etc. In a similar way that we applied the lever rule to phase diagrams containing microconstituents like the eutectoid, we can do a similar thing here. So let's have a look at these problems here and solve them. So let's have a look at the first problem. Compute the mass fractions of pro-eutectoid ferrite and pearlite that form in an iron-carbon alloy containing 0.35 weight percent carbon. Okay, let's take our zoomed in version of the phase diagram. I'll take this one as it's less cluttered. If you like, what I can do is use this one so you can see it in context of what we're doing. So I'm going to take this, I'm going to save that as an image. Call it example problem 3. Okay, so we've got a 0.35 weight percent carbon. So we have to draw that line. So we can estimate that this is the 0.5, so it would be somewhere along here. All right, so we're going to say that is 0.35 weight percent line. And we want to compute the mass fractions of pro-eutectoid ferrite and pearlite that form in the iron carbon alloy. So as we cool the austenite, okay, we're going to hit this phase boundary here where we're going to start to see the formation of alpha. As we cool further down, we're going to assume the cooling rate is such that we form pearlite and that there isn't enough time for further separation or further development of the microstructure. So what we can do is make the assumption that the phase composition at the eutectoid temperature, which is given by this horizontal line here, is going to be the same as that what's retained at room temperature. So when we do that, if we want the mass fraction of pro-eutectoid ferrite, so mass fraction of the alpha phase, which is ferrite, what we want to do, we need the size of this lever here. Okay, we're interested in the mass fraction of two phases. Let's have a look what we got. What are the two phases? We've got pro-eutectoid ferrite and pearlite. The mass fractions of these two must add up to 100%. So when we draw our tie line, we want to look at the composition of the alpha phase, which is right there, which is 0.022. And then the composition of the microconstituent, which is 0.76. This is the composition of pearlite. So we want to, if we want to find the amount, the mass fraction of alpha, we need to take the length of this line, B, which is going to be 0.76 minus 0.35, and divide by the length of the tie line, which is 0.76 minus 0.022. Zero 0.76 minus 0.35 divided by 0.76 minus 0.022. And here we get 0.56, which is 56%. Now, of course, if we want to know the amount of pearlite, which is the eutectoid, let's have a look how it's, it says pro-eutectoid ferrite and pearlite. Okay, so I'll call that pearlite. This is the pearlite composition. And pearlite is the eutectoid. So if you're confused between where to draw the tie line, the best way to do it is to think, what two phases am I trying to find the weight fraction of? Okay, those two weight fractions must add up to 100%. And so my tie line must extend from the composition of the first phase, which in our case is pro-eutectoid ferrite, and the second phase, which is that of pearlite. Okay, so that's what we've done. Well, the weight percent of pearlite, we know that these two must add up to 100%. It's going to equal 100% minus 56%, which is 44%. Okay, so we've done that. Now let's look at the second problem. In the second problem, we've got the microstructure of an iron-carbon alloy consists of pro-eutectoid ferrite and pearlite. The mass fractions of these two constituents are 0.174 and 0.826 respectively. Determine the concentration of carbon in this alloy. For this, let's use the detailed view. Over here, we can just use this one. This is fine. Okay, we just want to take this much. I'll save that as an image. And I'll also copy it. Okay. So we've got pro-eutectoid ferrite, so we know it's a hypo-eutectoid composition, and pearlite. The mass fractions of these two microconstituents are 0.174 and 0.826 respectively. Okay, so we add up these two numbers, they make 1. That's good. Okay, so determine the concentration of the carbon in this alloy. So we see that the pro-eutectoid ferrite the amount of that is pretty small. So what we expect then is that we're quite close to the eutectoid composition. And how do we know that? Because we know that the tie lines the tie line needs to go from the eutectoid composition to the composition of ferrite. When we use the level rule, this will be our distance A, and this will be our distance B. The amount of ferrite is going to be B divided by the total length of the tie line. So what we know is that the mass fraction of pro-eutectoid ferrite, so mass fraction of the alpha phase, okay, ferrite, is going to equal this distance B. Remember, it's always the opposite side, in the sense that if we have a tie line and we want to find the mass fraction of alpha phase, then we need to use the length between the average composition and the distance to the other phase boundary, or in this case, the composition of the second phase that we're interested in. In this case, not a phase, but a microconstituent. Okay, so we want B over A plus B. And we know what that value is. That value is 0.174. Okay, or in other words, 17.4%. Okay, so let's call this composition C sub 0. Okay, well, what is this distance B? Well, we know from the previous problem that the composition of the eutectoid steel is 0.76. So B, because this is 0.76, B is going to be 0.76 minus C naught. And A plus B is going to be 0.76 minus the composition right here, which is, if we go back to the previous problem, 0.022. And we know that this must equal 0.174. So now we can see that 0.76 minus C naught, and let's evaluate the bottom part, which is 0.74, okay, to a good enough rounding error. Yeah, that looks good. So this is equal to 0.174. So therefore, 0.76 minus C sub 0 is going to equal 0.174 times 0.74, which is 0.129. Keeping the working to 3 decimal places or 3 significant digits is plenty. So therefore, we can see that C naught is equal to 0.76 minus 0.129. .76 minus the previous answer gives us 0.63. And this will be weight % carbon.